We were talking about fluids on structures. I won't reiterate ad nauseum, but to just make the points again, the forces, the resultant force we get from looking at the depth below the surface of the centroid of the component. Let's see if I can do this. Beep. How slick is this? So, let's see if I can. So, I was going to make a point. I will make a point again in a second. So remember, this is the depth of the centroid of the plate below the surface. It's actually not so easy to do, right? So, I mean, I want to be able to use this. So this is the surface that the fluid is acting on. The centroid of this, actually, you can probably see it much better in real place rather than on photo booth. The centroid of this plate is the balance point of this plate. That is not where that force will act, but that's where you calculate the magnitude of the force from. If you want to calculate the point of action, then we can calculate it from the in-plane depth along the plate to where the resultant acts, and that is at some point slightly below the depth of the centroid, the y-coordinate of the centroid. And so one way to perhaps look at that, it doesn't seem so useful to do it the other way. So one way to look at that, I think, is to just understand that if we draw pressure in this particular way, and we look at the depth, which we'll call positive y, right, in everything we've done. Y, of course, can be inclined, which is the same as our negative z. Remember that. We haven't used this here, but that's the convention we've used. And if we look at the slope of this curve is equal to the pressure times, actually y times the unit weight of the fluid, which has been water. And so the point that we've made is that to be able to calculate the fluid pressure on a structure that is applied over some height, right? Then we can calculate the magnitude of the force from calculating h sub c, which is equal to a half of h in this particular case, right? But the point at which it acts, if this thing intersects the surface, the magnitude of this is Fr. And we know that the depth which this force acts, which is yr, which I can't really draw in here very well, but let's draw it over here, is equal to 2/3 of the height, right? And we rationalized that last time by this little, I'm not going to use photo booth, it's kind of not very good, I don't think, right? You don't get the three-dimensional, I guess that is what you don't get, right? You don't get the three-dimensional perception that your eyes allow you to give because you're viewing it plastered onto a screen. So the idea of this is that if I take this and I look for the natural balance point of this pressure distribution, it's 2/3 from the top, 1/3 from the bottom. That's what it is. And so the point where this particular force acts is equal to 2/3 down. Only if it intersects the surface, only if it's a flat, planar structure. As we go down further, I guess I've lost my notes now. My notes are on here, but maybe I can wing it. If we go down further, and we take the same depth change between a top and a bottom, and we're looking at the force that's applied on this plate, then again we can calculate the magnitude of the force, which would be equal to these two amounts, right? So let's call this top here y0. So this whole length here is going to be equal to y0 plus this length here, which is h over 2. And of course this magnitude here is equal to what we've called height of the centroid, right? The centroid of this plate is in the middle of it. Again, if I unwrap this, it's the same plate that's here. It just happens to be at some depth below the surface. The centroid is still in the same physical location. It's at this point. It's half of this height. And so this h over 2 is added to the depth. And so the depth of the centroid is y0 plus h over 2. But the location where it acts is no longer this 2/3, right? And the reason for that, you could surmise, is because if you divide this pressure distribution up into this, well, actually, let's do two things. Let me back off from that. First of all, the reason that you can realize that we can use the centroid to calculate this depth is exactly this, right? And that is that if you look at this pressure distribution at this half-point height, if you look at a dotted line, which I can't draw very well here, and you extend that dotted line up here, then basically you can take this prism here, and you can put it here, and then if you calculate the pressure at the midpoint, this magnitude here, in other words, which goes up to here, then that's the pressure that you use. So that's the reason why you can use this expression for the vertical depth always, even if this plate is inclined, by the way. And so that's the reason for that. I'll remove that because it makes it, I realize you might be drawing this at the same time. But the other reason for showing this is to make the point that you can divide this distribution up into two parts. One, which is this vertical distribution where there would be a resultant that you can imagine from the previous argument, the resultant for the square, we talked about this at the end of last period, is right in the middle of this, pardon me. And additionally, the resultant for this triangle is 2/3 of the way down. And so if we wanted to, as we did, I think in our parting stages last time, we could take moments about any point. You could choose this point here, or you could choose this point here. For this force and this force, we know the moment arms. You resolve them, and you could find the moment arm of the resultant force, which is equal to F triangle plus F square, right? Just the sum of those two. And so the reason for mentioning that is that you can see from this that the resultant acts 2/3 of the height down in this particular case. In this particular case, the weight of the pressure distribution is on this one that works halfway down. And so what you'd think is that as you get deeper and deeper, the resultant will actually move closer and closer to the center of the centroid of the plate, right? And you can tell that from this expression, right? Because the depth where this acts is going to be equal to the y-coordinate of the centroid, which is this point here, plus some amount. When you're right at the surface, this is a constant. It's just a function of the shape of the plate it's applied on. This is the depth of the component, and this is equal to the area of the plate. So this is a magnitude. The only thing that changes as you go deeper is how deep the centroid goes. So as the centroid goes deeper, this term will become smaller on the left-hand side. And so in the limit, as you go really deep, basically this little triangle will be so inconsequential compared to this big uniform distribution that it'll have no effect, and therefore the point of action will basically be at the centroid of the plate. And so that's all by way of saying that that's the case. So you can always rationalize that. You could also rationalize that on taking the pressure distribution up at the top of that, which we said if the balance point for this pressure distribution is 2/3 down, 1/3 up. Yeah, I don't know how good I am at origami. If you do it so it's representative of the pressure distribution, that's not quite right. It's a whole new bent on live performance art here. So at depth, this is the pressure distribution without the triangle on it. This is the pressure distribution with the triangle on it. And so now, if you look at where that pressure distribution will balance on this point, right? This is the pressure acting horizontally. The balance point for this, well, certainly if it was for this, it would be right in the middle. But when you add this additional pressure distribution, it's slightly to the left of that, right? Slightly down from that. So that's the rationale. So you can use these expressions always for the cases that we'd like to look at. I won't draw the diagram again, but you can remember it from last time. This, what happened? Oh, did I go too many? Don't want to give you whiplash, but this is the diagram, right? H sub c to get the depth, the fluid pressure is the vertical depth below the surface. If it's an inclined plate, then the depth, the distance in the plane of the inclination from the surface to the center of the plate is the y-coordinate of the centroid. So, important stuff. And the rest, the derivations we did were all just to give those expressions. So you can always use those expressions. Okay? Bless you. We talked about how you can do that to get the position of the resultant relative to, the depth in the fluid. You can also do it horizontally as well, and we did an example with that. I didn't mean to scribble that out. Whoops. You can also do it horizontally. Okay. So what I want to do today are a couple of examples to talk about fluid pressures on structures, then talk about buoyancy, depending on how much time we have. And so the plan for looking at these examples is to kind of not go through them numerically so much, but talk about the important features of them. I think that's most useful. So we're moving from plane structures, flat planes, flat plates, to looking at structures with curves on them. So why are we doing that? Is everything we've done irrelevant? Well, of course it's not. So the question here is calculate the resultant forces that act on this half-filled drainage pipe, which is filled with water up to its surface, and to figure out what the resultant force is that acts on this free body diagram. And so you can take the free body diagram and look at the individual forces. You have the weight of the water acting downwards. You have to have that reacted against by some vertical force. They must equal to each other, right? Equal and opposite by just the fact there are only two. And the horizontal resultant force, the only component that acts horizontally, is going to be the pressure that acts on this side here. We know that pressure distribution will look like this. We know that it intersects the surface. And so we know that this height here is going to be 2/3 of the depth, the radius, I guess, in this particular case, which is equal to 2 feet. I said we'd never do anything in English units, but I lied, I guess. Doesn't matter. So if we want to get that, we can calculate the center of pressure, centroid of this. The centroid of the plate. So we can get the force that acts horizontally, which is equal to the unit weight of the fluid, water, the area that it's applied on, the area here, to say how long, 1 foot length. So this area is going to be 1 foot times the radius, right? This height here times 1 foot into the board. And the height of the centroid is not where the pressure acts, but it's going to be half height. Which is HC, right? So this is going to be 1.5 feet. Okay, 3/2. Okay, so you got the force that's acting. So we have used something that we've done. We've used our understanding of the force on this. This happens to be a plate of water, but we're applying the force that stops it from rushing over us to the left. I guess your left and my left. So the weight of this, what's the weight of this? Well, the weight of this is just going to be pi r squared divided by 4. This is equal to the cross-sectional area of the pipe. So this is equal to area of quadrant, I guess, right? I suppose it's also multiplied through by 1 foot, because this is an area times a length is a volume times the unit weight is a force. And so you get a force from that, which is the vertical force. And so we know that this horizontal force resolving horizontally, they have to equal each other. I guess this up here. We know that the vertical force has to equal to the weight. And so if we wanted to know the direction at which that acts, we have two force vectors, force horizontal and force vertical. and the resultant of those is just this. And so the resultant is just Pythagoras. So that's, we know the vertical reaction, we know the horizontal reaction, we know the vector sum of those reactions, the resultant, in other words, which is F sub r. And the other thing that we don't know but you could surmise is where it acts. We know that everywhere along this contour, the fluid pressures are acting perpendicular to this circle, and so they must act through this point here, and so by definition the resultant of these must also act through this. So if you want to calculate what the resultant is, it has to act through this point, and it has to be of magnitude F sub r, which is parallel to this amount here, and you know what the amount is from this. So you know the magnitude of the force, you know the direction in which it acts, and you know where it acts, physically where it acts. Okay? Sometimes that's important. Okay, so that's what we're trying to do. Yes, sir.
I got lost a little bit with the area for F sub 1. Where is how would you repeat where it's in?
So the area that we calculate is if you draw on this, if you look at 1 foot into the board, this length here is 1 foot, and this length here is 3 feet, and so the area should be 3 feet times 1 foot.
Okay, so it's just a double triangle.
Yeah. It's a square, not triangle, right? So it's a square. It's the depth of the culvert, this water field, which is 3 feet,
Yeah.
and upstream 1 foot. Yeah. Okay. All right. So that's where it intersects the surface, and so you can do those calculations. What happens if it doesn't intersect the surface? How do you do the same calculation? It's similar. Again, you can take a free body diagram, a little esoteric in this case. You're just finding a resultant. Why do we want it? I suppose you might want to know it if this was a gate that could flap open. But you could do the same calculation once again. What's different? Well, the only thing that's different now is that the fluid pressure here is not zero because it's not a free surface. And so that brings a couple of ramifications, right? The first ramification, I suppose, if you tried drawing the pressure diagram, is that the pressure diagram would look like this, where this amount here has to be equal to exactly the same pressure distribution here. Right? So this is what we have. So you have a fluid pressure working on the top. And this fluid pressure is going to be what? Well, actually, we don't need to do the fluid pressures, but you know the fluid pressure is going to be equal to the unit weight multiplied by H sub A. But we don't need that because we can use another way to get it. The other way to do it, of course, would be to calculate what F1 is, which we can do straight away. And F1 is going to be what? It's going to be the unit weight of the fluid, the height of the centroid of the plate, times the area. The area of the plate is going to be, well, let's just write it out. Unit weight, the height of the centroid is what? It's this plate. It's this water surface that we have here. So it's the centroid of that plate, which is just going to be bang slap in the middle of it, right? Because it's just a rectangular area. This area here on the top of the plate is just rectangular area. So the centroid has to be at the depth H sub A. And the area has to be the length AB multiplied by let's call this W. There has to be a width into the page. So that's it. So we can calculate from that. We want to know what the magnitude of F2 is. So we can think about this distribution, but I guess what we know from this distribution is that we know that the resultant of this fluid pressure isn't going to be working at two-thirds the depth anymore, right? Because we have this distribution. And so we just need to note that that's the case. We can calculate what that is from, I guess I don't do it here, but we can calculate that from our expression for YR is equal to what? The the second moment of area about the centroid plus the area times the depth of the centroid divided by AYC. I guess this is squared, right? I think. Should remind myself just so I'm not... Yeah, so it is. Just rearranging that expression. And so what are each of these magnitudes? Well, we get this value of IXC. Can you remember what that is? It's equal to B cubed A over 12, as I recall. B cubed is this depth here, so it's equal to HC minus HA, all cubed, multiplied by the width into the page, divided by 12. Okay. Standard result. The area of that is going to be equal to what? It's going to be equal to HA minus HC. I guess I didn't really mean to go into this kind of detail, multiplied by W. So it's the depth of the plate that's on the... So we have this semicircle on the right-hand side of this. So it's the depth of this plate, which is HC minus HA. It's multiplied by the width here. And so that's just that area. And YC is going to be the depth of the centroid of that plate. The depth of the centroid of that vertical plate is the midpoint. And so the depth of the centroid is going to be... Anyone want to tell me? Right? So it's equal to this depth here plus half of this length. So this is Y sub C right here. Not the point where it acts. And so we know from what we said before that we'd expect that this resultant F2, so this is what we're trying to calculate, is F2. The resultant we can also calculate from just this expression as well. I didn't mean to, so I might as well do it everything. I know I'm writing all over the place here. So the horizontal, just write it out. F2 is going to be equal to what? It's going to be equal to the unit weight of water times the depth of the centroid. The depth of the centroid is actually YC in this particular case, because YC is equal to HC. Perhaps I should have written I will write it the other way around. And multiplied through by the area of the plate. And so you have the area of the plate. It's actually, if this is circular, then both AB and AC are the same. So I guess the area would be what we called length AC multiplied by W. Nothing more than that. Okay? And so we have the force magnitude acting horizontally. We have the force magnitude acting vertically. We can calculate the weight in the same way as we did before. It's just the area times the area times the width into the page, which is the volume times the unit weight. And if we have that, we have everything we need to be able to calculate these components. We know that resolving horizontally, FH equals F2. And we have magnitudes for both of these. Well, we then have magnitude for this. If we know F2, we know FH. We can resolve vertically. We know what the weight is. We know what this vertical force is. And so we can calculate FV just by writing FV being equal to the sum of those two. Always take directions. FV positive upwards has to be equal to the two components acting against it. So we know this and this, so we can calculate this. If we know what the magnitudes of these two forces are, we can calculate the resultant. And if we know the resultant, we can calculate exactly where that should act. And for the same reasoning as before, because all of these components act perpendicular to this, we could actually take moments about a random location to be able to figure out what that is. We know where this one, we know where F2 acts, we know where F1 acts, and we know where the weight acts, and we could take moments about any point, or this point, to be able to determine. Let's not do that now, because we'll do that in the next example. Okay? So I guess that's illustrated the point that, you know, you have to be kind of mindful of not just assuming. Now, you can use these equations. The two equations we've used are this and this only. And so long as you know what the parameters that go into those, you can do that straightforwardly, right? Everyone with us? Okay. Yeah, so a tainter gate, as it's called. This is actually a tainter gate in Nova Scotia. It's not a very good picture. It's a Xerox of a photograph. But a tainter gate is exactly the lightest possible gate that you could have to be able to hold back water. It's an arc, and so the idea is you have a flow. This would be upstream, and you can lower this gate to block this particular channel. And the reason you can make this gate very lightly is because all the forces act through perpendicular to this circular arc, and so they all act through the pivot point, and so you can make it very lightly to be able to accommodate that. And so a tainter gate is just a typical gate that's used. Won't talk about that. This one's too complicated. This you'll never be asked to do in an exam or anything else ever. So let's leave those. And let's just do a couple more. I'm going to do this one. I won't go into it in huge detail, but I'll try and talk around the important features. So this is a boom or something that's sitting next to a lip. This boom is floating on, in this particular case, in oil. I have no idea what this thing is, but it's just a contrived figure. And the question is, ask what the reaction is of the force that's applied by this physical thing floating on the wall is. And so, as in all the things that we do, we can define a free body. And the easiest free body to take is something that's a square in this particular case. And these, of course, will have some weights attached to them, but we don't care. We're only asked to calculate what the force is horizontally. So anything that's orthogonal to that will have no influence on the horizontal resolution of forces. So we don't care. So we're not going to bother with those components. So what we have to do is write some kind of free body diagram to look at pressures. Also, by the way, there'll be a pressure on the bottom acting up here, which we don't care about either, because it's obviously resolved in the wrong direction for us, and so we don't have to mess with that either. What we do have to deal with is the fact that we expect to have a fluid pressure on the side of this fluid. We know how to calculate this because F1 is equal to the unit weight times the depth of the centroid times the area. This thing here, if I can do it in bold, is the area. The depth of the centroid is half h, if this whole thing is h. Well, let's not call it half h. Let's call it radius, right? No, let's call it half the diameter, because then it makes sense, right? This is the centroid, which is the centroid of this plate, and therefore we can use this. So we have that force. We're probably not going to have to resolve moments because we only have lateral forces to resolve. We want to find out what Fa is, which we don't know. And so what's the magnitude of F2? Well, this is a tricky one, right? So what would you think? You might think, for instance, that F2 would be this, because this could be atmospheric here. And it could be that. But if it was that, for instance, then that means that the pressure here, this length, is much less than the pressure here. And so there has to be some flow that would be coming out of here. And that's perhaps not the case. And so you have to use what you know about, what do we say? change in pressure with x is equal to 0. So if you go from one point to another point in the fluid, same elevation, the pressure here has to be this. So the pressure at this point here has to look something like this, where this amount here is going to be exactly the same as equal to this. So this P is going to be equal to the diameter of this times the unit weight, and the pressure here has to be equal to the diameter multiplied by the unit weight. Right? Bless you. And so when you're calculating the fluid pressure that would be applied here, the centroid that you'd want to use would be this. So HC2 is going to be equal to no, sorry, not that. It's this, right? HC2 is going to be d over 2, which is the distance to get to this point, plus d over 4. Complicated way of just saying it's the half height of this length here, right? But you can calculate what that is. And so that would give you the pressure at this point. Actually, if you think about it, if you stop it. I removed something, I'm not sure what. If you think about extending this curve up here, you'd find out that it actually hits the surface. I'm not sure how well you've drawn that. But basically the distributions on both sides would be the same, except you're missing this little window here because it's air. But the pressure at this point has to be physically the same pressure as you go across this thing here. And actually you could also justify that from the fact that this expression here says that if you can move from this position on this side of the cylinder all the way through the water to get to the same, whoops, I can't do it, to this position on this side of the cylinder by going through the same fluid, the fluid pressure physically has to be the same. So that's the little interesting wrinkle in that. So same principles. So even though we're talking about curved surfaces, you realize we're still using the equations that we use for forces on plane surfaces, merely by making the free body in the way that we've made it. Okay? So let me skip out of this. This is an exam question last year, and I'll go through this. The solutions are online. It's a question that was ostensibly out of the book. You'll see that if you look at the exams, there's a PDF without the working in it, which is the final exam is given. There's a PDF with the solution in it, which is the exam as I worked it, and maybe I decided to lose some of the questions. I think in the exam as given, the last question says, if you can solve this equation, this problem to calculate the weight of this gate without doing the other steps, then you get 100% for the question. So, which is, I think, fair. But the way this is it just leads you through the question to be able to get you to define the solution. So here's the view. So this is a gate which has a pivot here. The gate has this semicircular quadrant, half hemispherical. No, it's not. It's a cylinder. Quarter quadrant of a cylinder, which has some weight. It has water on the upstream side, and the basic question is, how big does W have to be to keep this gate closed? Just. And so you have to figure out what the forces are on this gate. You have to figure out where they act, and then ultimately you have to do the calculation around the correct pivot point to be able to figure out what the value of W is. That's basically it in a nutshell. So walking your way through this, I'll go through it moderately quickly. Calculate the weight of the gate in the first place in terms of the unit weight of the gate material. We've already done that. The area of this multiplied by the length into the page. 1 meter, I suppose. I can't remember exactly. Yeah, I had to define the length into the page. 1 meter, I'm guessing, W. It would have been defined properly in the final question as given. So area times length into the page times unit weight of the gate material gives you the weight. What happened? What is the lever arm of the weight on the gate? What is the resultant force on the gate? What is the vertical force? I'm just going to look at those. Let me draw them on the gates. So where does that lever arm work? Well, the lever arm for this works at the centroid of the gate. And the reason for this little diagram is that you know that the point where that lever arm works is the center of mass of this particular thing, right? Because it's the same as if I had a quarter circle here and I balanced it on my finger, then that would be the centroid for that. And just the standard result is this, that we know where that is. So this is the length here that we would use. So this is L gate, scaled appropriately. What are the horizontal and the vertical forces that are acting? So the horizontal force would be given by what? Fr is equal to the unit weight of water times the depth of the centroid for the horizontal part times the area. What's the area? The area is equal to the radius times the depth into the page. The depth of the centroid is going to be equal to, this is 1 meters, so this is going to be 4 meters down and half a meter up. So in other words, we're going to draw a free body. Ooh, that's interesting. Moves the whole thing. So we're going to draw a free body that isolates this portion here. So the height of the centroid of this plane is going to be 4 plus half of this distance. HC1, HCR. This is going to be what? 3.5 meters. 4 meters minus half. And there's going to be a fluid pressure acting up. And we can get FV from the same. FV is going to be equal to the unit weight of water multiplied by the depth of that centroid multiplied by the area. What's the area? It's the area of this surface, so it's going to be equal to the radius times 1 again, or W into the page rather, which is 1. The depth of the centroid, it's the depth of the centroid on this plate. This is the plate. Halfway along, has to be right in the middle. Doesn't matter, it happens to be in the middle. It could be anywhere. You know it has to be in the plate, but it happens to be in the middle. So the depth of the centroid here is going to be equal to HC vertical. So this is equal to 4 meters in this particular case. So we have the location of the horizontal force. I guess maybe that it's not the resultant, is it? It's the horizontal resultant force. We have the magnitude of the vertical force. Now if we want to be able to resolve exactly whether this dam opens or not, or the gate opens, we need to figure out the locations. Okay? So let me scoot off this page. You can go back to the video if you haven't got everything down. So the lever arm for the dam itself, we calculated. The horizontal resultant, we calculated. The vertical force acting upwards, we calculated. But we didn't actually calculate the resultant, right? Because what we need to do is we need to be able to figure out exactly what the resultant force acting on this body is. And the easiest way for us to do that is to be able to take the pressures acting on this free body, which include not only the magnitude of this fluid pressure acting upwards, but also the weight of this small slither acting downwards. And so one way we can do that is we can calculate the magnitude of this. This is what we've calculated already in on the previous page. We can calculate the water, which is just going to be equal to this area multiplied by the depth into the page multiplied by the unit width. And this area is just r squared 1 minus pi r squared over 4, right? Just the area of a square with a quarter circle cut out of it. It's the part that's left. The square is going to be r squared, and the circular part is the part that's left. So this is the area of this little shape that looks like this. And this is the area, obviously, not obviously, but of the circle. And this is the area of the square. So this minus that equals this, right? And so we have just by summing those, we now know what this is because it's the volume times the unit weight. And we end up with a vertical force that we have applied. So it was a bit more complicated than I wanted. That's why there were bonus points attached to it, and that's why people had as long as they wanted to do it. But anyway, so we have a magnitude of this resultant force. Calculate the inclination of that force is just by doing FV and FH as a resultant, and you can get this inclination. You know it acts through the center of this location, and so you can ultimately take moments to be able to figure out exactly what those are. And so the point is that in this you can get all but the very last 10 points just by doing these plug and chug things, calculating force vectors, etc., using these two equations we have for where forces act and the magnitudes of the forces. And then ultimately you have to resolve around this particular point for the resultant that you have acting and the weight of the gate which you want to determine, right? So this is what we know acts, and we need to be able to calculate resolving around, actually not this point, resolving around this point. We need to take moments about this point to be able to figure out what the moment of this is relative to what the moment of the resultant is. So, again, more involved than I want it to be, but that's the way it is. Okay. What else? So, and the book's solution is a different solution, but comes out with roughly the same answer. So I guess that went on a bit longer than I wanted. So we've talked about forces acting on structures. The other thing that we can also talk about is buoyancy. Buoyancy is kind of important because it is also a resultant force that acts on a structure, and we can do exactly the same thing as we've done previously, and that is we can look at forces that act on this particular geometry. So if we, for instance, drew a pressure versus depth diagram on this, the basic idea of buoyancy is that if you look at the fluid pressure acting on the top of this structure versus the fluid pressure acting on the bottom of this structure, then you can surmise that one is larger than the other. The reason it can be larger than the other is because you have a weight of this which provides the extra thing that you're reacting against to be able to hold it up. Same as a ball, right? So it has some weight attached to it. And so there's no force applied to the top of this ball, but clearly there's a force I have to apply on the bottom of this to keep it held up. And the rationale for that is that it's this weight which is the reason for this pressure, and so they exactly balance each other so they're in equilibrium. If you remove this weight from the interior of this by just carving out a hole, then all of a sudden you have an excess pressure on the bottom of this thing, and that's what buoyancy is. That's why things want to rise in water. And so you can do this very simple calculation, which gives you a very straightforward result that just says that this out-of-balance force that's applied is equal to the unit weight times the volume of fluid displaced. The unit weight of the fluid, by the way, not the solid, and it's Archimedes' principle, which you all know. And so you can use that in the same way with the other things that we've done to be able to do calculations on stabilities of structures. Maybe I have these wonderful videos. Don't pack up yet. I've got to see this. We haven't had much of a reason to be talking about fluid mechanics today, but maybe we do now. So what I will do is we'll look at this, refresh. So, buoyancy. So submarines, you know how they work. You want to go underwater, you take on water as ballast. You make sure you have some compressed air, of course, to be able to do something with it. The water changes the weight of the submarine, and therefore it goes down with depth. You displace the water out of the tanks, and it rises to the surface. So this very spectacular breaching sometimes goes wrong, of course. Now we don't want to not put this into a social context. When was this? 2001. Oh yeah, you're definitely alive for this. So this was one of these emergency egress things out of the depths, where a U.S. submarine offshore from Hawaii, I think it had Tipper Gore, Al Gore's wife, on board at the time. And it comes up, and of all the places you could choose to come up out of the ocean, it comes up underneath a Japanese training ship training fishermen, young kids, actually people not so different from age from you, I would guess. And it sinks it. Both the submarine survives, the Japanese training boat doesn't. The Japanese training boat goes to the bottom of the ocean, and a number of people were unfortunately killed in all of this. So we can use this idea of an out-of-balance force to be able to evaluate the force that acts on structures. So in the same way that we calculate resultants, for instance, to calculate whether a gate opens, this is also an extra additional component that would act on submerged bodies. I suppose the only important thing to remember is that this buoyant force is really an out-of-balance force that we have to restrain, and that the unit weight that we're dealing with, again, is not the unit weight of the material that's removed from the system, but it's actually the displaced fluid and its volume. So it's just Archimedes' principle. In this particular case, there are no lateral forces. You can imagine there are no lateral forces because if you take this little differential cube, you have exactly the same forces acting oppositely on either side of this, the resultants. So there is no net force horizontally. And the other important thing to remember is that the point of action of this force acts through the center of volume, if you like, the first moment of volume or area. And so in a cube, it would actually be the centroid of the volume. And so in this particular case, it would be the midpoint, but also in the middle of this. So the centroid of a rectangular prism, for instance, would just be where these two lines cross, which is no different from actually, if you could actually physically put your finger inside this, drill a little hole and put a needle inside this and support this on a needle, this would be the balance point of this homogeneous material. So it displaces fluid, which is homogeneous fluid, and so it has to be, even if this structure were made of different materials and the density changed from location to location, it would be the center of the centroid of the displaced mass. In other words, if it was all a homogeneous material. Okay? You can do more rigorous analysis to look at things that aren't rectangular volumes, but the result becomes the same, and it's an absolutely inviolate relationship that the buoyant force is just equal to the volume displaced multiplied by the unit weight of the fluid. So those are the 2 points to remember. You calculate this force from this simple expression, and it acts through the centroid of the displaced volume, and we call that the center of buoyancy. Nothing more. Okay? So how do we apply that? Well, you can apply it as a free body just in exactly the same way as we've done in the past. And the idea here is that if you have a buoy that is, or a buoy as you might call it, that is anchored into the seabed or the bed of a lake, then we can look at the tension that you have to apply in this cable to be able to counteract the buoyant force of the displaced water and balanced by the weight of the metal structure that you have with the air inside it in this particular case, which actually wouldn't register. So you have a weight that you have applied, you have a buoyant force, and you have a tension in this cable. And in this particular example, the question is, what is the tension in the cable that gets applied to this? The reason for the tension in the cable is that the net force acting on the bottom of the underside of this hemisphere is larger than the net force acting downwards, and so there's a net buoyant force. It's nothing more than that. And we can always calculate that just from the unit weight of the water in this particular case multiplied by the volume of this spherical component. So resolving vertically in the downwards direction, we have the tension in the cable plus the weight. In the upwards direction, we have the buoyant force. We know exactly what the buoyant force is. We can calculate the weight because we're given the weight, and so the only thing to be able to calculate here is the tension in the cable. So we put in some numbers for that. If we know the volume of the buoy, then that's the displaced volume, which is 4/3 pi r cubed. We know the unit weight of water, in this case seawater, which is slightly more dense than fresh water, which would be 9.81, right? And the weight of this is given, and the remaining component is to calculate the tension that's in the cable. And it comes out to be 9.3 kilonewtons. We know that the tension acts directly through the center of pressure of this buoy, just from the resolution of all these forces. The weight acts through that location, the buoyant force acts through that location, and therefore the cable also has to be aligned that if there's to be no net moment in this. Okay, so it's relatively straightforward. So the other thing that then relates to this is the idea of center of pressure and center of gravity of the displaced component, because these relate, for instance, to stability. Now we're looking at stability before in this example. Do we have it still? If I get rid of this, see if this will open. Maybe it is one of these. Sailboat. So see if this will actually spark up. So here we have a bit more difficult situation, right? All the examples we've looked at so far. All the examples we've looked at so far have been of a completely submerged body. Here you have a body which is partly submerged. And so stability is one of the issues that relate to buoyancy forces. And the problems get a bit more difficult when you have things which are only partially submerged, because you have a portion of the structure which is kept outside the water. And of course, the submerged volume changes as you heel over a certain degree, depending on the wind in this particular case. And so the magnitudes of buoyancy in these particular cases change. So we can look at the issue of stability. So if we do that, let's come back to look very straightforward at this and what we know about this. So certainly the easiest cases we have to deal with are for fully submerged bodies. And the reason for that is that they always displace exactly the same amount of fluid, right? So both of these bodies are completely submerged, and therefore the buoyant force which is acting is always the same magnitude. It's not going to change in magnitude, but also act at the same place. So the center of pressure, the center of buoyancy for this particular structure is always going to be the centroid of the volume. And it's always going to be in the same place because the shape of this volume doesn't change. So it's always going to be directly, it's going to be on an axis which comes down through here, and also the other axis as well. The center of gravity, for instance, in this particular case, would be a situation where there's a denser material in the bottom, because the center of gravity here would also be the same place if this was a uniform density material that was inside, submerged in the water, say cork, which is lighter than water, mainly air. But if it's denser, but if it's something where, for instance, most of the load is in the bottom half, then the center of gravity is below the center of buoyancy. And so if you take this stable structure and you move it somehow so that this center of gravity is moved to the left, and you leave it, then the couple, or the moment that's applied by this, is this force acting up through here, center of gravity pulling down here, and so they will tend to self-right. They'll self-align themselves. And so in this particular case, if you have the center of gravity below the center of buoyancy, then it's intrinsically stable. If you have the converse, if you have the center of buoyancy which is below the center of gravity, maybe as in the case of the sailboat we just looked at, then if you slightly move the center of gravity to the right, and as a result the center of buoyancy to the left, then all of a sudden now the force acting downwards and the force acting upwards gives a net moment to this, which disturbs it, and it trends to put it into, actually it will ultimately turn it into the condition on the left, right? So there's intrinsic stability which is involved in these. And so it's relatively straightforward when you have submerged volumes. And I think the easiest case to look at, if you can look at an obvious case, right, is if you take a container and you fill the top container with something has a mass of 2 and the bottom which is nothing, and it's 1 by 1 by 1. You can do all the calculations. And if you look at the center of buoyancy, and if you look at the center of gravity for each of these two situations, it's not very difficult to figure out exactly where those locations should be, right? Center of gravity, you can take moments about any point on this, and if this is 0 and this is 2, you know that the center of gravity is only going to depend on, can't do it well. It's going to be in the centroid of this second part. So this is going to be the center of gravity in this particular case. If you look at the center of buoyancy in this case, then it doesn't care about the relative densities or the masses of these two components inside this. It sees a displaced volume in the upper part, a displaced volume in the upper part, in the lower part, and so the center of buoyancy is going to be, in this case, it's just going to be the centroid of this displaced water volume. And so that basically is this case where you have intrinsically unstable. If you happen to give it a small displacement, so these aren't quite in alignment, in this case they're absolutely in alignment, it's absolutely stable. But it's conditionally stable because if you give it a small motion to the left, someone moves around in the ship or it gets pushed by a wave, then the net couple that is applied by the moment between the center of gravity acting downwards and the center of buoyancy acting upwards rotates it until it finds its new stable position, and the new stable position would be this geometry here where one is below the other. And so that's, you can imagine that that's basically the case of what's going on. So that's only made a little more difficult by the fact that if you have floating bodies which have a free surface attached to them, then you can imagine that as the wetted perimeter of this, or the wetted volume, the volume, if you like, which is below water, changes. If the cargo in this particular ship is always fixed, then you'll have a center of gravity which will always be in a particular location within that ship. So if the cargo is not moving, which is one of the reasons you want cargo not to move, of course, is that you actually have a fixed center of gravity. But the center of buoyancy is going to be determined by the displaced volume. It's almost a square area here, so in this particular case it should be roughly, as you can see, where exactly it is. But if it rolls for some reason, because there are heavy seas and it has inertia from the last wave that went past, all of a sudden this isn't a rectangle anymore, And actually, probably not a bad estimate of where the center of gravity would be. Well, the centroid of this is actually, if you can draw a line through here, and if you can draw a line through here, well, no, it's not quite the case. Perhaps I should rescind that point. The center of buoyancy will be on the centroid of this submerged volume, where that is. And in this particular case, the center of buoyancy, which is acting upwards, and the force acting upwards, and the center of gravity with the force acting downwards, intrinsically tends to right this ship, which is what you'd like, right, if you're traveling on this. If you have the case where, for instance, you have a really very high center of gravity, as you may do in a sailing boat, that's one of the reasons you have a keel with some weight on it, is to try and move the center of gravity down. Then in this particular case, the opposite happens. Here you have a small movement to the right. As you move to the right, then the line of action of the weight and the line of action of buoyancy give a moment to it which continue to overturn the structure. And as it overturns, it becomes more and more out of kilter, the moment gets larger, and ultimately it would realign itself in some way. I imagine in this particular case, the resting position would be something like this, right? Or maybe a bit down, but certainly now you have a center of buoyancy which would be given by this point here, acting upwards. Your center of gravity here would be somewhere off here. And so what it would do is it wouldn't be quite horizontal, but I'd imagine that this line here would be slightly down, and it would be slightly tilted like this, as you can imagine. But anyway, so you can use that to be able to talk about stability. So it all revolves around the fact that the buoyant force, which is always equal to the unit weight of the fluid that's displaced multiplied by its volume, acts through the center of buoyancy. That center of buoyancy is always the centroid of the displaced fluid mass that's present in the system. Okay. So there is one example that's attached to that. Go through it very quickly. I think the question is, you have a pressurized tank. In this tank, you have a weight, a block, that has a certain weight attached to it. You have an air pressure which you apply here, and this block is holding down a plate. This air pressure, of course, acts against the upside of this plate, and the question is, how big an air pressure do you have to apply such that this plate is just about to lift? The maximum air pressure you can apply before you lift this. And I suppose the interesting thing to realize about this is that if you look at, for instance, this weight, we know that if we draw, for instance, the fluid pressure and how that fluid pressure changes with depth, then the whole idea of buoyancy is that if the pressure here is atmospheric and this is the fluid pressure distribution, then the mismatch in fluid pressure between the top and the bottom, which probably shouldn't use delta P here, let's not use delta P, they just use P. The difference in pressure between the top and the bottom is equal to some amount given just by the height of this, right, and the gradient. And you know it well. In this particular case, delta P would be equal to this height multiplied by the unit weight of the fluid, whatever the fluid is, water in this particular case. If you increase the pressure in this tank so that it's acting on this surface as well as on this surface, then all of a sudden all you do is you change this inclination here, but now this line is exactly parallel with the other one, and so the difference between the upper pressure and the lower pressure is again equal to delta P. And so what doesn't change is the magnitude of the pressure of the water acting top and bottom in either of these cases, and that basically says that this is the reason for buoyancy, and so the buoyancy doesn't change either. And so you can just use the buoyant weight. So I think that's the observation. So the question is, what's the magnitude of the fluid pressure you have to apply that causes this plate to come off? And if you know what that fluid pressure is, how does that register as a length on this manometer, which is just a manometer part of the question. So again, the fluid plate, the failure mode is for this to physically move up, and so you can resolve vertically. So the forces you have acting vertically are the fluid pressure times the area of the plate. You have the buoyant force of this submerged weight, which doesn't change as a function of the fluid pressure. And you have the actual weight of this material that's acting down, not the buoyant force. And so you can resolve vertically. If you resolve in the vertical downwards direction, downwards is the weight, upwards is the force due to the fluid pressure over an area and the buoyant force. And you have some of these. So you can write this expression in terms of the weight, which is just going to be a unit weight multiplied by a volume, unit weight of the solid. This pressure is going to be an area, which is the pressure, this is the area of the plate. And the buoyant force is going to be the unit weight of water in English units and the volume of that displaced amount. If you know these, you know everything except for the magnitude of the fluid pressure, so you can calculate that. And so now you know the fluid pressure that will blow the top off here. For the arguments that we've applied here, it's just the buoyant weight that you need. This pressure differential top and bottom really is the reason for buoyancy, the buoyant force. And if you know what the pressure is, then you can calculate the pressure change just from this manometer, because you know that this pressure here of the air, sorry, I won't write that. Here, the pressure of the air has to also equal the pressure of the air here. And so you can write P air minus, if we write this here, they've used delta H for something else, so we'll use this as delta L. So pressure air minus the change in length multiplied by mercury, unit weight of mercury, has to equal the pressure of the atmosphere. We're going to take this pressure as 0, and so we know this magnitude, we know the unit weight of mercury, so we can calculate delta L, and just from trig we know that 30 degrees, what's this, delta H and delta L, so in other words delta H equals sine 30 delta L. So we know everything here except for this length. We can calculate this length since we know so we know everything here except for this length. We can calculate this length because we now know what that is. So if we know what delta L is, we know what this angle is, we can calculate what the length along the differential manometer is, or the inclined manometer is, which gives us this extra resolution, if you like, in terms of measuring this. And hopefully that's the expression that we have here. Yeah, so this is just substituting in for the terms that we have, and you come out with the length that gives you this maximum pressure that it can withstand before it blows off the top. So that's our exposition, if you like, of fluid pressures on structures, and by inference also fluid pressures that relate to buoyancy. There's a very small set of expressions that describe the behavior that we're dealing with. They're summarized here. The resultant force is equal to unit weight times the depth of the centroid of the plate below the surface, vertical depth, times the area over which it acts. We can always resolve forces if we have vertical and horizontal forces through their resultant, which is just Pythagoras. Although the magnitude of the fluid pressure resultant is given by this, its point of action is not through the centroid of the plate in which it acts, but it acts at the location in the plane of the plate, a distance from the surface, the fluid surface where the pressure is equal to 0, equal to y sub r, and that magnitude of y sub r is given as the location of the centroid of the plate plus some small additional distance. And that small additional distance depends on the shape of the plate that we have, which is embodied in this, and also how deep that plate is relative to the free surface. If it's really shallow, we have some standard results which we can use. 2/3 of the depth, for instance, for the location of the center of pressure on a plane, a rectangular area that intersects the surface. And physically, as we go deeper, this first term becomes less and less significant, and the point of action of the force approaches the centroid of the plate. Certainly if it's a horizontal plate, it is always at the centroid of the plate. And if we want to be able to look at the stability of a structure, we have to resolve forces around a failure mode. So those are the three lessons, if you like, from fluid pressures on structures. Magnitude of the resultant, where it acts, and collectively if you have forces and you want to look at the stability of a structure, whether it's the roof of a plane that is unzipping or whether it's a gate that you're trying to open up with forces, you need to resolve around some prescribed failure mode. And so out-of-balance forces on structures are also applied by buoyancy, and the magnitude of the buoyant force is just equal to the unit weight of the fluid, which is displaced, multiplied by its volume, Archimedes' principle, and it acts through the centroid of the displaced mass. So in kind of a corollary to this, the magnitude of the force comes from this, but it doesn't act at this depth of the centroid, it acts at some other location. Likewise, the magnitude of the buoyant force is given by this, and it acts always at the center of the displaced fluid volume, and which is really just its centroid, and we call that the center of buoyancy. Buoyancy, and this is the center of pressure. They're analogous in some way, but they're different. Okay, so we'll leave that there. All right, thank you.